a brief overview of the approach that we use in our studies to derive phenomenological, to analyze phenomenological properties of models with asymptotic safety. And I call this approach effective, since it allows us to make these phenomenological studies without remaining to the great extent agnostic about the details of quantum gravity calculation. So just as a disclaimer, this is not going to be the quantum gravity talk, it will be the phenomenological talk. And then in the main part of my presentation, I will discuss two applications of such understood asymptotic safety. And the first application is to enhance predictivity of new physics models, of certain new physics scenarios that may be interested for us phenomenologists for different reasons. For example, since this model can address some experimental observables or experimental anomalies that cannot be explained by the standard model alone. And in this setup, what asymptotic safety does for us, it provides us with a set of boundary conditions at or around the Planck scale. And these are boundary conditions for a priori free parameters of these new physics models. And I will discuss it on a case study of the mu1g minus 2. And in the second part of my talk, I will discuss another application of asymptotic safety. And namely, I will show you that in this framework, there exists a very nice, very robust, dynamical way of generating in a natural way small quantities, small couplings in the framework of quantum field theory. And as an example of such application, I will discuss the issue of small masses of the neutrinos in the standard model. And then I will conclude. Okay, so what is asymptotic safety? To understand this, we should think a little bit about possible asymptotic behavior of the dimensionless couplings of our quantum field theories, couplings that show up in the Lagrangian. And both in the standard model and in the framework of most BSM, beyond the standard model scenarios, there are two behaviors which we are familiar with. One is the so-called asymptotic freedom, very characteristic of the quantum chromodynamics, which means that when we increase the renormalization scale, when we increase the energy at which we measure this coupling, the value of these couplings is decreasing, which means that in the deep UV, this coupling essentially leads to the Gaussian non-interactive fixed point. And this is a feature of a theory that we liked, because it means that such a theory is well-defined and well-behaved at an arbitrarily high scale, and it can be considered fundamental. On the opposite side of the spectrum are the theories which are described by U1 gauge symmetry, like for instance, quantum electrodynamics, whose couplings are known to increase with the energy, in an unstoppable way. So sooner or later, they would reach their Landau poles, or in other ways, they would reach the regime where they become so non-perturbative that the theory breaks down. And of course, it cannot be considered fundamental. We need some extra description on top of this. And this is something that we don't really like. So asymptotic safety is to some extent an extension of the concept of asymptotic freedom to such asymptotic behaviors of the couplings in the deep UV, where they develop a fixed point, so their value stabilizes at some point and it doesn't change with the renormalization scale, but this value is non-zero. It's actually, the value of the coupling is different from zero, so the theory remains interactive. And this is what's called asymptotic safety. Theories with such feature are called asymptotically safe theories. So this idea has been first proposed by Weinberg in the late 70s as a way of making the gravity, four-dimensional theory of gravity, non-perturbatively renormalizable. But in recent years, asymptotic safety has been quite extensively used also in the framework of Young-Mills theories in normal quantum field theory as a way of curing pathological behaviors of the U1 type gauge couplings, like this one, by making them reach at some point in their RG flow the fixed point of this kind, interactive fixed point. But from the point of view of phenomenology, what is particularly interesting about the existence of such a UV interacting fixed point is that its properties can be, to some extent, transmitted down to the low energy regime and lead us to some phenomenological predictions. So in this context, what we need to understand, the main characteristics of the fixed points are related to the issue of the critical exponent and critical surface. So if So if we want to analyze the property of the fixed points, whether they are in UV or ER, we need to calculate the so-called stability matrix. This is just the matrix of the derivatives of the beta function. We calculate the negative of its eigenvalues. And these are called, this negative eigenvalues are called the critical exponent. So in a simple one-dimensional case, if the critical exponent is positive, we know that such a fixed point characterized by positive critical exponent will be attractive in the UV and repulsive in the infrared. The coupling associated with such a critical exponent, which we call relevant, and such couplings would be free parameters of our theory, because running from top to bottom, so from high energies down, we are not really able to predict the infrared values of this coupling. Any of the infrared value is okay from our point of view, because if we reverse the RGE flow and we go to the UV, we will always end up attracted to our initial fixed point. The situation is quite contrary for the negative critical exponents, for which the fixed point, which is the fixed point is infrared attractive. And this means that no matter what is the initial value of the coupling in the UV, its RGE flow will always end up attracted towards the fixed points while we decrease the renormalization scale. And such couplings, which are called irrelevant, would constitute a predictions, because this infrared, the value related to the infrared attractive fixed point will always be fixed, no matter what was the initial value in the UV. So in more realistic theories, we usually have Lagrangian that are characterized by more than one coupling. And what happens in this case is that all relevant couplings in such a model would span the so-called critical surface. And the critical surface, illustrated on this plot, is the only submanifold in this full coupling space on which the physical trajectories can reside. And by a physical trajectory, I understand a trajectory that would connect this UV fixed point with the infrared. And what is important about the critical surface is that all the irrelevant couplings, which may also be present, and we would like them to be present in such a model, can only deviate from the fixed point along the critical surface. And this is illustrated by this green curve here. And this have very important consequences for what's happening in the infrared at low energies, because it means that as long as we have a way of determining the low scale values of all the relevant couplings in our theory, for instance, measuring them experimentally, which would mean we can choose one particular and specific trajectory on a critical surface, then all the irrelevant couplings in such a theory will be uniquely predicted, uniquely fixed. And this is exactly this predictive power of asymptotic safety that we were interested in our studies, and we wanted to apply it to some phenomenological analysis. So there are several ways that theory can be make asymptotic safety, but what we were doing in our investigation and what I'm going to talk about today is asymptotic safety, which is induced above the Planck scale by the quantum gravity effects. And this setup, I think, is quite well justified, as there exists a huge and still growing set of theoretical evidence that quantum gravity does develop indeed a UV interactive fixed point. So the idea dates back once more to Weinberg and his and his postulate to make quantum gravity, his theoretical postulate of making quantum gravity a theory that is asymptotic safety, but it has been first really calculated in 4 dimensions by Reuter and Zawersik at the 8 of the 90s. And by considering a very simple gravitational action, that the so-called Einstein-Hilbert action, that has only 2 operators in the action, the Ricci scalar and the cosmological constant, a system that is then described by 2 gravitational couplings, the Newton constants, and once more the gravitational constants. So Reuter and Zawersik showed that such a system indeed can develop 2 different kinds of fixed points. One, the Gaussian, where the both gravitational couplings are 0, here, that would correspond to the low energy regime of the gravity, where the gravity essentially decouples, its effects are negligible, and we don't need to consider it if we do particle physics, for example. But that such a system also, they showed, allowed for another fixed points, UV interactive fixed points, at which both gravitational constant and cosmological constants are not 0. And this fixed point is here. And this fixed point would actually correspond to this high scale regime, well above the Planck scale, where the gravitational interactions become important. So as I mentioned, the first calculation was very simple. It's for a very simple gravitational action. After that, there has been a lot of activity in the field. Many papers and new and more elaborated calculations showed up, which proved that such a fixed point is not really an artifact. It's not just some artifact of simplification, maybe, of this action, but it really persists there. Even if we start to add more operators of higher order operators to this action, if we do use a little bit different calculational techniques, if we start to couple such a gravity with matter, such a fixed point always persists. But from our point of view, what is even more important is that if we are in this regime where gravity becomes strongly coupled to matter and where its interaction become important, the graviton fluctuation do generate extra contribution to the matter, to the beta functions of the matter coupling, gauge, Yukawa, Quartic couplings, which will be parameterized in this talk by these objects called Fs. So in principle, these guys can and should be calculated from first principles, for example, using the techniques on functional renormalization group. Here I am showing you one very particular and specific example of how this parameter Fg can look like. Don't get used too much to the exact form of this coefficient. What I want to show you is that it does depend on the gravitational couplings. So now you can immediately see that the moment the gravity reaches its UV interacted fixed points, G and lambda jumps on their fixed point and stay there, this Fg provides us with an extra constant contribution to the matter beta function, which becomes important above the Planck scale. And this can have very important consequences for the asymptotic behavior of the couplings, which is illustrated on this plot. So let's imagine that this is some gauge coupling of a U1 symmetry, and this is on the x-axis is the renormalization scale. So if this parameter Fg is smaller than some critical, the value that we call critical, which just is obtained by setting this equation equal to 0, which means that the graviton fluctuation are less strong than the fluctuation of all the particles of matter particles of the system. The model is not really helped by gravity in the sense that these trajectories still run into the Landau pole in the deep UV. So such trajectories we will call unsafe, UV unsafe. On the other hand, if the gravital fluctuation becomes so strong that they can overcome the fluctuations of the matter particle, the theory can suddenly become asymptotically free in the UV due to these contributions from gravity. And this is a good news because it really allows us to save many theories that otherwise we wouldn't be able to consider fundamental. But there is one very specific value of this quantum gravity parameter Fg when it's equal exactly to F critical. So when this equation is equal 0. And this is exactly a case when our theory would become asymptotically safe. So this gauge coupling in the presence of gravity would develop an interactive UV fixed point. And this is what I am going to talk about on the next slides. So I told you that this quantum gravity contributions to matter beta function can in principle calculated. The problem is that these calculations are marked with very large uncertainties that stem from different quite technical assumption that needs to that needs to be done on the way to be able to calculate anything in the FRG setup, like for instance number of operators in the gravitational action, the cutoff scheme, etc. At the end of the day, it has been shown also in many studies that these uncertainties can reach even 100%. So we don't really know the precise value of gravity contribution to the meta function. Therefore, an alternative approach has been proposed in the literature that we also use in our study, is to treat the gravity contribution as free parameters that needs to be determined by matching our RGE flow that runs from the UV down to the infrared, by matching it to the known low energy data. So to explain you the algorithm, let me show you a very short, simple example. So let us consider as the standard model extended by just one extra U1x abelian symmetry factor. And let's consider just the running of the hypercharge coupling and this new GX coupling. So the way this all will work, this determination of the gravity parameter will work is the following. So we know the measured value of the hypercharge coupling down at the electroweak scale. This is this number. So what we do, we run it up to the Planck scale. And at the Planck scale, we make this fundamental assumption that due to quantum gravity, our gauge coupling will develop an interactive UV fixed point. With this assumption, we know the value of these fixed points directly just by reading the matched value at the Planck scale. Once we know the value of the fixed points, we can determine numerically the value of this gravity parameter that should be consistent with such a running. And then we use the other very important property of quantum gravity contributions to the beta function, which is the universality of gravity contribution. Universality means...
Excuse me, why it has to be constant after the Planck scale? Why?
That's the assumption. That's the assumption that we make. We assume that we want our theory to develop an interactive fixed points due to quantum gravity. And if there is, with this assumption, it means that the value of the coupling will not change because it will be the fixed point.
Okay, thank you.
Yes, so I said that the gravity is universal in the sense that it doesn't distinguish between the internal degrees of freedom of matter, which means that this gravity contribution Fg will be the same for all the gauge couplings in the theory. And if that's the case, and this seems something that is really very justified also by explicit calculation in quantum gravity, then we immediately can read off the fixed point value of this new physics couplings. We can run the system down and we can read its value at the low scale. So that is how the asymptotic safe predictions will work. Okay. So this kind of a construction is particularly useful when we deal with some new physics models that we want to employ to explain some experimental measurements or experimental anomalies. But these experimental observables that we want to address with these models are really not enough to constrain the parameter space of such a model. So at the end of the day, by explaining one anomaly, we are not really able to pinpoint, for instance, very precisely the mass of our new physics. And that's where asymptotic safety can help us. So let me discuss this more in a little bit more detail on one example. And this example is the anomalous magnetic moment of the muon. So as you know very well, already 2 years ago, Fermilab collaboration measured the anomalous magnetic moment of the muon, and their measurement confirmed the previous result of the BNL collaboration from Brookhaven, almost 20 years old result. Both results are perfectly consistent with each other, and if we combine them together and compare it to the standard model determination of mu1 g-2, then the discrepancy between theory and experiment is above 4.2%. And this is a very strong evidence that we may be facing some traces of new physics here. Of course, right now we know that there may be some caveat in this, in this reasoning. In recent, especially in recent year, many lattice study has popped out, which seems to be showing that we may be underestimating the standard model prediction for the g-2, that the standard model value may be actually slightly higher, and this discrepancy would decrease. But for a moment, until this is not resolved, taking this number as a face value, obviously we need some new physics to explain the experimental value of g-2. So there is a class of models which are very useful for this purpose, and these are models that extend the standard model by extra fermion and scalar fields. And these models are extremely well known. There is the whole physics behind them is perfectly well established. What is important is that their contribution to g-2 can show up in two kinds of diagram. The first diagram on the left-hand side is where the chirality flip of the muon happens on the external leg. And these models are really very minimal. They only require 2 extra particles beyond the standard model, but it is also well known that these models first have some theoretical issue with the Landau poles of Yukawa couplings that show up relatively low. If we run our couplings, the predicted or couplings necessary for g-2 to higher scales. But even more important, the masses of these new physics particles are so low that by now they are all excluded by the direct searches, new physics searches at the LHC. So this kind of diagrams we can forget. They do not really work. On the other hand, this kind of diagrams where the chirality flip happens at the internal loop works very well. As a matter of fact, this diagram is parametrically enhanced so much that we can really push the masses of the new physics couplings so deep into the TeV regime that all the LHC bounds would be easily avoided. And on one side, it is a good news because it means that these models work very well as an explanation of mu1 g-2 anomaly. But on the other hand, the emerging new physics parameter space remain largely unconstrained. As an illustration, let me show you an example here on this plot on the left-hand side. This is a model that contains one real singlet scalar and 2 vector-like fermions, singlet and doublet under the SU2L symmetry. On the x-axis, you can see the mass of the scalar, which in this case can also play the role of the dark matter. That's why it's called M dark matter. And on the y-axis, you can see some combination of the new physics couplings that we have in the scenario. And the parameter space consistent with the measurement of g-2 is shown in dark blue and green. And you can see that this parameter space is enormous. It spans many orders of magnitude in the coupling and many orders of magnitude in the mass of new scalar in this case. And this is a little bit problematic in the sense that we are not really able to pinpoint a mass of new physics in this model. We cannot go to our experimental colleagues and tell them, build us a new accelerator, a new machine that would be able to test, I don't know, the scalar at 1 TeV, because the scalar can be at 1 TeV, but it can also be at 5 TeV. It's perfectly consistent with g-2 in this kind of scenario. So this is a little bit a problem, this very wide parameter space, and we would like to find some ways of making it a little bit smaller, making the model a little bit more predictive. We can think on different ways to deal with these problems. We can, of course, try to add more constraints, experimental constraints, and to see if the parameter space can be reduced, maybe by some complementary experimental analysis. Doesn't work that well. If, for instance, in this model, if we add on top of the G-2 also the requirement of having the correct relic density of dark matter due to our dark matter scalar, you see that the parameter space, the green one, is not really much smaller. We can also think about reducing the number of free parameters in such scenarios by, for example, adding some extra symmetry, like for supersymmetry. In supersymmetry, we know that very similar is a perfect example of a theory with extra fermions and scalar, which has this nice feature that the would-be Yukawa couplings in supersymmetry are not really free parameters because they are related to the gauge couplings through this extra symmetry, supersymmetry between bosons and fermions. And finally, we can think about making our models UV complete, and this UV completion hopefully would provide us with some high-scale boundary conditions of our a priori free parameters, mainly the Yukawa couplings of our Lagrangian. And that is where we will use the idea of asymptotic safety about the Planck scale. So just to make clear what kind of model I'm going to talk about, here is the Lagrangian, the new physics part of the Lagrangian. So I consider here two different pairs of vector-like leptons, and by different I mean they transform differently under the SU2. That's necessary to create this chirality flip in the inner loop of the G-2. So these leptons are called E and F, and there is also an extra scalar S. H is the standard model Higgs. So what is important here is that in such a setup, there are 4 a priori entirely free Yukawa coupling in this model. And now we would like to try to find out if we can restrict the initial values of this Yukawa coupling somehow with asymptotic safety. And to do this, we assume that we minimally couple such a model to gravity above the Planck scale. So as you can expect now, the consequence of this is that above the Planck scale, the beta functions of the gauge and Yukawa coupling would receive the contributions from quantum gravity, parameterized by our parameters Fg and Fy. As I say, universality works here, is in place here, is the same parameter Fg enters the beta function of all the gauge couplings, and the same parameter Fy enters the beta functions of all the Yukawa couplings in the theory. So now the strategy is, as I mentioned already before, we determine the value of the gravity parameter Fg by matching the flow of the hyperjudge coupling down to its measured value. We can, in exactly the same way, we can fix the value of the parameter Fy by matching the value of the top Yukawa coupling, which is also measured experimentally down. Once Fg and Fy are determined, all the new physics Yukawa coupling that we also assume that they develop a UV interactive fixed points, we can read the value of these fixed points here. There is no ambiguity here. These values are just given by the quantum numbers of our vector-like fermions and scalars that are in our model, and we run the whole system down at the Planck scale. Yes?
Can I ask a question?
Yes, sure.
This universality that you mentioned, is it an assumption or is it from some prediction? Some theory?
This is an assumption.
An assumption that you're taking. Okay.
This is an assumption, but this is an assumption that, first of all, it sounds very reasonable because we do expect that gravity is only, the gravitational interaction should be only sensitive to the mass, but not sensitive to internal degrees of freedom. Yeah, so in this like basic concepts seem to make sense, but it's also confirmed by calculation in the FRGs. In the FRGs, there are, especially for these parameters Fg, there have been many calculations of these values, of this not Fgs, but the graviton contribution to the beta functions, and they all confirm that this gravity contribution are really universal.
Okay, thank you.
So we run the system down to the low energies, and we can read the predicted value of all 4 Yukawa couplings that we have in this system. Now, these M's here, they correspond to different models we considered in this paper, and these different models are characterized by different transformation properties of vector-like fermions under the SU2. This is not so important. What is important is, I would like you to notice that this prediction can be quite different. For example, this Yukawa coupling Y1 between model M1 and M2 can differ by order of magnitude. And this is entirely, once more, let me emphasize it, the consequence of asymptotic safety. About the fact that we have this interactive fixed point in the UV, whose value is determined by the quantum numbers of the participating fields. And it also has very important consequences for the phenomenology. So let me now tell you several words about it. So after we fixed all the Yukawa coupling, new physics Yukawa couplings by this asymptotic safe ansatz in the Planckian regime, the only 3 parameters that we're left with are the masses of the scalar and fermions. And here on the left-hand side plot, I am showing you the parameter space for model 1. Here are the quantum numbers of the fields that are associated with model 1 for the fixed scalar mass 100. This scalar in this model cannot be really heavier than that. And on the X and Y axis, you have the masses of vector-like fermions. So now the parameter space consistent with G-2 is shown here as this red stripe. So this is the good parameter space. And on top of this, we also superimpose some experimental constraint from different experiments. For example, this gigantic gray region is the bound from the measurement of branching ratio Higgs to mu plus mu minus by CMS. It's a relatively new result from 2019, but it's very important, especially in the models that explain G-2 with the chirality flip. In orange and blue, I show you the results from the direct new physics searches by the LHC, the exclusions by Atlas in this case. And if we insist of having good dark matter candidate, the only region that is allowed is marked in green. But what I wanted you to take as a message from this plot is that we can now, we started in phenomenological models, we start with this gigantic unconstrained parameter space. Here, what happens that at the end of the day, we can predict 2 out of 3, we can predict very precisely the masses of the new physics particles. The scalar, we know it's around 100, but you see, you can also read off the mass of the vector-like fermions, whether in this region or this region. We essentially make a very exact prediction where the lightest of these vector-like fermions should be. And this is something that we can tell experimentalists, and they can try to look for it. And such a model can be easily, or less or more easily, experimentally tested, can be verified whether it makes sense or not. Here on this plot, I'm showing you the predictions for model 2. Here are the quantum numbers of the participating particles. The important thing is to notice that this parameter space consistent with G-2, this red blob here, it has a totally different shape, and it corresponds to totally different masses that in model 1. Actually, the masses here of these new physics particles are below 1 TeV, and this is entirely a consequence of the fact that this Yukawa coupling Y1, which is responsible for how strong the chiral enhancement in the loop is, that this Yukawa coupling is so much smaller here. So these 2 examples show you that asymptotic safety not only allows us to enhance predictivity of new physics model by fixing the dimensionless coupling and then making it much easier to make precise prediction for the masses of the new physics particles, but it also can give us some way, a handle of discriminating, also experimentally, between different models that without this boundary condition would look to a very similar phenomenology. So I think this is a quite cool property of asymptotic safety. Okay, this game can be played also for other experimental signatures for the B2S anomalies that unfortunately now seem to be disappearing, B2C anomaly, dark matter, baryon number. If you're interested here, I quote some papers that did analyze it in the past. But to finish this part of the talk quickly, I would like to comment on one issue that is very often raised when, and there are also many questions that we always have about it when we present this result. How robust are our asymptotic predictions for the new physics couplings, given the simplifying assumption that we make in our effective approach? So I didn't really go through this assumption explicitly. Let me maybe summarize them quickly for you now. So our analysis is always done at one loop in the matter sector. The Planck scale is set quite arbitrarily at 10 to 19 GeV. The gravitary parameters Fg are assumed to be constant above the Planck scale and 0 below the Planck scale, and this decoupling of gravity happens instantaneously at the Planck scale. Yes, so at this black line, we have some non-zero Fg above and 0 below. And we know from the FRG calculation that that is not what is really happening. We know that this transition, this flow from the gravity UV interacting fixed point down to infrared is not instantaneous. It happens over several orders of magnitude, and this is illustrated by this purple and red lines. That is the actual running of these gravity parameters in a specific truncation. So the question is, does this thing can affect our low-scale predictions for the new physics couplings? And this is something that we've been analyzing very recently in Warsaw. The paper about it is going to appear very soon. I hope next week it will show up in the archive, so I invite you to see it when it's there. But just a disclaimer, let me tell you that at the end of the day, what we find out is actually quite interesting. We were able to show, and we are able to show in this paper, that these uncertainties can not only be well described, but they also are not so dramatic, especially in the gauge sector. All kind of uncertainties that can stem from dropping any of these assumptions are well below 1%. So really, this effective approach works really perfectly well in the gauge sector. In the Yukawa sector, we're talking more about uncertainties of the order lower than 15%. It's extremely model dependent. There are scenarios where it's of order several. The max we can get is probably around 15%, but it is still lower than most of experimental uncertainties that affect the observables that we would like to fit and explain with our new physics model. So that also tells us that even in the Yukawa sector, this effective approach to asymptotic safety seems to be working pretty well. Okay, so this was that for the predictions. I don't know, maybe you have some questions to this part. Because if not in the, yes?
Yeah, I have a comment, a general comment. I mean, since you know the uncertainties, why don't you just calculate the whole thing better? Because obviously the fact that you are freezing at the Planck scale, all the Yukawa couplings, etc., is a very strong assumption, because that's not what's going to happen, like you said, in reality. So why don't you go ahead and calculate the behavior beyond that and get the actual value in the real ultraviolet?
So that would be the thing to do, and hopefully it will be possible in the future. But here once back, we go back to this problem that initially motivated us to use this initial approach, mainly the derivation of this. There are a lot of uncertainties in derivation of these quantum gravity parameters. This running that I'm showing you here, it's a very particular truncation, very particular, some technical assumptions are behind this, and we are not sure that with more operators in the gravity sector, maybe with some non-minimal couplings between gravity and matter, that this running would look like this. So also right now at this moment, the FRG calculations come with uncertainties that seem to be much higher than the uncertainties related to choosing the simplified effective approach. So that is the problem here. Then on theoretical side, we are not really still able to we do not really have everything under control on theoretical side. And that was the main motivation for the effective approach.
So you are saying the Wetterich equations still are not completely, I mean,
Yes, there are. So the Wetterich equation is a perfectly known equation, and it's well established. The problem with it is that to calculate anything with Wetterich equation, you need to start simplify it, and you need to make a lot of different, very technical assumptions. Now, sometimes different all well-justified assumption can read to the predictions for this gravity contribution that can differ by 50–60%. So that's the problem, that we are really still not able to handle everything theoretically in a convincing way. And of course, if these parameters of G as calculated by different groups, for instance, doing the FRG calculations would differ by 50%, that also our low scale prediction would be differing by maybe even more than 50%, which would be much more than this estimated uncertainties from using the effective approach.
okay, thank you.
Mm-hmm.
I
Okay,
have a
so
question. Sorry,
yes.
so I have a question. So can your study explain the gravitational waves or constrain gravitational the observable parameters?
Yes, in principle, yes, the same game can be played with gravitational wave. This is actually something that we're also working right now with a collaborator from Warsaw University. We would like to apply this framework to some models that are able to generate observable signatures in the gravitational waves. Yes, so in principle, yes, you can use it to any new physics model you want.
Then from the study, actually I'm quite new to this field, so my question would be very naive. But what kind of observable is the strongest prediction in your study? What kind of parameter or the observable?
But which one? The one that I discussed? This was G-2. That was the main thing that we wanted to.
If your study can be connected to the gravitational waves or the gravitational
okay, can we come back to this question at the end, because I'm not sure how much time. I'm afraid I'm running out of time here, and I still had one little topic to discuss.
Okay, sure.
Yeah, so okay, here so I need to accelerate quite a lot now. So if you give me 5 more minutes, I should be done. So I wanted to show you how asymptotic safety can not only be used to make predictions for the new physics couplings, but also how it can provide us with a quite nice, I think, dynamical mechanism of generating small parameters. And as an example, I'm going to use the neutrino masses. So just make the whole story very short. If we put together all the experimental information about the neutrino from oscillation experiments and from the measurements of CMB by Planck satellite, that's in the end of the day, we end up with this kind of plots that tells us that the neutrinos are lighter than 0.03 electron volts. So now the question is how to explain such a small mass of neutrinos. The easiest thing would be to treat neutrino at exactly the same footing as all the other fermions in the standard model, generate their masses through the Higgs mechanism. That is perfectly okay. The problem is the Yukawa coupling that needs to be responsible for such a small mass is of this order, much smaller than for anything else we know from the standard model. And small numbers in physics usually are considered problematic if there is no fundamental explanation for their presence. So an alternative has been proposed many years ago in the type of many type seesaw mechanisms. Here I will just remind you the type 1 seesaw mechanism for the main logic. So what we do, we assume that neutrino is a Majorana particle and lepton number is violated. That allows us to write the Majorana mass term in the Lagrangian, construct an effective neutrino mass matrix, and the light neutrino masses then are given by this expression, which means that now we can have neutrino Yukawa couplings of order 1 at the price of having extremely heavy Majorana mass of the order of 10 to 13, 14 GeV. give or take. So now I would like to show you what asymptotic, if we want now to embed the standard model and right-handed neutrino in asymptotic safe setup, what can it tell us? So let us consider a very simple systems of RGE. We have only hypercharged top and Yukawa coupling. You will later see, for a moment, believe me for a word that this is enough to understand what's going on. I will at the end show you the full result for the full standard model, and I will show you that it works exactly the same. So quickly looking at the beta function of neutrino, you can see that it allows two fixed point solutions, one interactive and one non-interactive Gaussian. So let's take a closer look at both of them. So if we would like to have a neutrino at the fixed point that is non-zero, that is an interactive fixed point, this can be done, of course, by canceling these two terms. One is positive, the other is negative. However, by determining the value of fixed point value of GY and Y top, we know that these contributions are of order 1. Therefore, the only natural value for the neutrino Yukawa coupling is also of order 1. If we would like to obtain the Yukawa coupling of the order of 10 to minus 13, which is what is measured experimentally, we would need to cancel these two contributions with extremely high precision. And this immediately cries fine-tuning. As a matter of fact, the amount of this fine-tuning is quantified on this plot on the y-axis versus the expected Yukawa mass. So this is not a good solution. It's a super fine-tuned solution. We don't like it. To explain Yukawa masses in this setup, we need a seesaw after all, so asymptotic safety doesn't gain us much here. So let us take a look on the fixed point at which the Yukawa coupling is 0. So it turns out that if this value of gravity parameter Fy is smaller than a certain value, which I call F critical, and this is its numerical value, it depends on the quantum numbers of all the participating particles, then this Yukawa coupling becomes irrelevant. And it means that if it sits at this fixed point, it would also always stay at this point. That's what the relevant means. That it, in other words, that 0 Yukawa coupling for neutrino is our prediction. So in principle, this is also not a good solution unless the system allows for other fixed points that could prey the laws of the UV fixed points, and then this guy could be an infrared fixed points, an infrared attractor of the trajectories of neutrinos. And that actually is exactly what happens in this simple system, and it's illustrated on the plot when I show you the phase space for the neutrino and top Yukawa couplings. So what is the arrows points to the UV. So what is going on here? So this fixed point F here, it's exactly this fixed point at which neutrino Yukawa coupling is 0, our irrelevant fixed point. But in this system, there are also other fixed points allowed, fixed point G and fixed point E, at which are UV attractive fixed points. So what is happening right now? The setup is the following. We assume that in deep UV, the gravity would generate one of those fixed points. Let's assume it's fixed point B. And then when going down with the energy, we will be following this trajectory, which is always attracted towards the value of neutrino at 0. So this is the attractor, infrared attractor at 0. And that is exactly how we can generate an arbitrarily small neutrino Yukawa coupling in the setup. It's all the other way. It's presented on this plot where you can actually see the actual running of the couplings. That's the renormalization scale. So starting with fixed point G, the blue line shows you the neutrino Yukawa coupling, the red shows you the top Yukawa coupling, and you can see that the moment the top Yukawa coupling jumps at its fixed point, which happens here, the neutrino Yukawa coupling starts to go down. And by choosing properly the value of the Planck scale, we can obtain as small neutrino Yukawa coupling as we want. So this is not a real prediction because we cannot predict the precise value of neutrino, but this is a dynamical mechanism of generating naturally such a small value. And in a sense, it can be considered as an alternative to seesaw, because as seesaw, it has one free parameter. In the seesaw is the mass of right-handed neutrino. Here, it's the position of the Planck scale, or the position of the Planck scale here along this trajectory. So this very simplistic picture works perfectly well in the standard model. We can add the Yukawa couplings of all the standard model fermions, and nothing bad happens here. It works exactly the same. Interestingly, we can also feed the angles of the PMNS matrix, so all the neutrino mixing angles. Note that we're not predicting them. It's not a prediction. We are just able to fit them because they would correspond. Yes.
In the previous slide, what's
Yes.
the theory from which you got this flow? What's your theory? I mean, what are you?
Oh, so this is a theory. So this is standard model with right-handed neutrino that is a Dirac particle in this setup. So Yes, it's a Dirac neutrino that couples to the Higgs boson and the lepton doublet. So it's exactly like the other fermions in the standard model, and it is coupled to gravity above the Planck scale. So we have this contribution from graviton, Fg and Fy above the Planck scale, and that is exactly what creates all these different fixed points. So this is really a very minimal theory. There is just one new particle with respect to the standard model, neutrino. And of course, the gravity, but gravity is unavoidable here. And
you're using a sort of a linearized version of gravity, or what? The total? So that's, yes. So that's exactly the. So it's, yeah. So this is the G. So this is once more this effective approach in which we don't really calculate the contributions from quantum gravity to the beta function, but we are able to determine them by matching the flow from the UV to the ER. So the only assumption that is made is the universality of this gravity contribution and linearity, in the sense that, as I showed you, as you can see here, if that's what you mean by linearity, is that these gravity contributions are always multiplied by 1 power of a corresponding coupling. So these are the only assumptions we're making here. Yes, this is this effective approach, but it is justified. Let me emphasize it one more, but precise exact calculations in the FRG. In the known models, these gravity contributions are known to be, it's known that we are able to parameterize them like that. Okay, so this mechanism works in the standard model. We are able to fit the mixing angles in the normal ordering case. We're not able to find any solution in inverted ordering case, which may be a very slight hint that asymptotic safety seems to be favoring normal ordering. And one final word is that this mechanism is actually much more generic. Essentially, it can be used in any BSM model that for some reason would require small parameters, small Yukawa couplings, like, for instance, model that explain the relic density of dark matter through the Friesen, or models with feebly interacting particles. These models usually require very small Yukawa couplings. And this can be easily arranged in such a framework with asymptotic safety above scale, just by introducing extra pair of fermions that would couple to some scalar field. And so we just need to create a Lagrangian in which we would have something that looks like a top Yukawa coupling, or would play a role of a top Yukawa coupling, so being the large coupling, the one that enters at the large fixed points, and the small Yukawa coupling that would undergo this behavior similar to what happens in neutrino in the standard model. And this is a condition that is usually that this new fields needs to satisfy to make it happen. So this, I think, is also quite nice possibility that can be explored in BSM model building with this asymptotic safety ansatz. So since I ran out of time here, I leave you with the conclusions, and if you have some questions, please ask now.
Yes, I have a question. What with the you showed that the neutrino Yukawa can be drawn to a very small value. What happened with the Yukawa of the charged leptons? I mean,
thank you. That is a very good question. I didn't have time to go into details. So usually here, but also in these models with G-2, usually if a standard model coupling is not mentioned, it means that it is assumed that it's a relevant parameter. So it means that it develops a zero fixed point in the UV. And by if you remember this plot that I showed you at the beginning, what does that mean that the parameter is relevant? It means that that we can always choose a trajectory emanating from a UV fixed point that will reach arbitrary low scale value, which means that if a coupling is relevant, there is really no problem with fitting it to what is measured by the experiment.
Okay, so it means that if you have chosen here the other fixed point, the number E, which is at 0, then that would look more like, say, the Yukawa of a charged lepton.
I'm not sure if I understood.
Well, you see in your plot of the renormalization group flow there, you have a red fixed point you call G and a green that they call E. And
yes.
That one has a Yukawa value at the high energy, almost 0.
Yes. So fixed point E would.
So that would work for the charged leptons or something like that. Huh?
Yes, exactly. Yes. So yes, that's exactly what happens. So for the charged leptons, the trajectory looks something like this trajectory that I'm showing you for top. Yes, that it starts at 0, and we can really adjust. We can choose which trajectory we want to reach the correct low scale value.
Okay.
Yes, but that's exactly what it means. In fixed point, G top is exactly relevant, and that is exactly what happens with other standard model fermions.
Thank you.
Can I do a small question? That's more technical. When you talk about that you are the connection from asymptotic safety from gravity from UV with infrared parameter, you have to define a scale there, or we can say a normalization point in the momentum. But in this case, from the point of view you are doing in this dimensional less or dimensional full variable. Because in one case you have to consider the anomalous dimension. I am assuming that you are not considering this variable. Yes. Because I don't see in any place the anomalous dimension for the gravity. Or you're assuming that is not relevant?
Yes. I'm not showing you the anomalous dimension for the gravity. As a matter of fact, I think the running of the blue line here, which I didn't comment, is exactly the running of the anomalous dimension of the graviton, which can be calculated, but no, in this effective approach that we consider, we don't consider it because we just don't calculate really anything in the framework of FRG. But yes, if you want to really calculate this precisely with FRG, this quantum gravity contribution, the anomalous dimension of the graviton also needs to be calculated. Yes, of course.
Okay, thanks.
I had a question, Kamila. In your analysis of the renormalization group equation, you showed that you were mentioned that the uncertainty in the Yukawa sector were larger than the gauge sector. What was the reason? Is on the output of the your analysis?
Yes, no, the reason is simple. Let me see if I can show you this somehow. Since it's a new result, I still don't have a backup for it, but maybe we can understand it. Okay. Yes, we can understand it from here. So look, if we determine the value of the gauge one loop, the value at the gauge coupling at fixed points, it's always given by something like this, of a square root of this FG parameter and some numbers. If we consider a ratio now of these two fixed points, Gx and G1 star, the dependence of FG will cancel out. So the value of the fixed point will be given, the value of the ratio of the fixed points for the gauge coupling will be given only by its quantum number. And this is the main reason that this dependence of what happened gravity gives us above the Planck scale cancels out from the ratio, and this is what keeps this ratio extremely almost an invariant of the RG flow when we run down, which actually you can even see here. You see that the distance between these couplings at the fixed point and down, it's almost the same ratio.
I see.
And that's exactly what makes this error for the gauge coupling so small. In the Yukawa coupling case, it's not so easy. I don't have a formula here, but what happens is that the fixed point value of the Yukawa coupling depends both on Fg and on Fy in a way that doesn't allow to cancel out this dependence. And that introduces, this is the main source of the uncertainty that stems from different sources. It stems from the determination of the fixed point. It also stems from the running of the Yukawa couplings above and below the Planck scale. But that mainly boils down to the fact that for the gauge couplings at one loop, the dependence on Fg totally cancels out.
Thank you, Kamila. More question from the audience?
Yeah, I have one more question. So here, you have covered the low energy observables such as muon GMAST or neutrino methods. So here, my question is more somewhat fundamental. So what is a good reason to connect this low energy observables to this high energy scales via the asymptotic safety? What is a good motivation, or what is the real advantage?
Main motivation comes from this plot. So in this plot, the parameter space of G-2, it's everything green and blue. And a priori, it's not a problem. It may be perfectly okay. If we're working with phenomenological models, there is not issue with this. But sometimes we would like to be able to constrain our model more precisely. For instance, we would like to be able to pinpoint more precisely the matter of the mass of the new physics particles, which cannot be done in the framework of simplified of phenomenological models. And for this reason, apart from the fact, so this is phenomenological reason, there is also theoretical reason that maybe, yes, I keep forgetting, but this is one of the main reasons to study this at all, is that the hypercharge coupling in the standard model do have the problem of the Landau pole. Of course, it happens above the Planck scale. We don't really know what may happen there. Here, the assumption is that the presence of gravity can actually heal this pathological behavior. So this is like the fundament on which then we build, but this enhancing predictivity through the presence of the interactive fixed points in the UV, it's also our strong motivation to make this asymptotic safe ansatz.
So do we really need the energy scale more than Planck, above Planck energy scale or something like that? Do we really need that
yes,
kind of energy scale?
if we want to, if asymptotic safety, if the source of asymptotic of the interactive fixed point is the gravity, then of course we need to be above the Planck scale. That's not the only possibility. There are also models which allows us to generate fixed points in the RG flow below the Planck scale, essentially with no gravity, with just a very specific particle content of the theory. So there are like things like that you add a big number of vector-like fermions, like the NF, and if this NF is large enough, it can be proved that in certain cases this can lead to generation of the no gravity induced fixed points at any scale between the TeV and the Planck scale. So there are different ways of imposing asymptotic safety that would probably lead to different phenomenological predictions.
Okay, thank you.
More questions from the audience? Cristóbal, please.
Hi, Kamila. Very good.
Hi.
So you mentioned that the uncertainties in the Yukawa sector are below 15% on page number 6.
Yes, like approximately, right? Yes.
Yeah. So my question is, do they include a running of the gravity couplings in the pure gravity sector, or maybe with no minimal interactions? Because I'm asking this because there are some infrared instabilities that can deeply affect the infrared behavior of quantum gravity.
Yes, so I hope this will be explained in detail in this paper that is going to appear next week. So yes, in a way, we did include this kind of effects, and we did it first by showing. So this paper will be quite technical and mathematical, but we managed to show that certain ratios of the couplings can be made invariants, or not can be made, they are just invariants of the RGE flow if the boundary conditions are dictated by the asymptotic safety, by the fixed points. And for instance, in the case of gauge coupling, it really shows that this dependence of FG cancels out to the point that no matter what happens with this FG, no matter how this FG really runs in quantum gravity, the ratio of the gauge couplings would stay almost fixed. And to some extent, the same can happens in the Yukawa sector. But yes, one of the big part of our analysis is to show how different functional dependencies, which we do not calculate from quantum gravity, but we try to assume very generic functional dependencies there exactly to see how this could affect our prediction, and we show that even if this gravity, the running of gravity parameter is kind of crazy things happen here, it really does not affect the predictions by more than 15% in most of the models.
Independently of what happens below the Planck scale, right?
Independently on what happens
independently of what happens below Planck scale. I mean, how they run.
Yes, okay, but below the Planck scale, this is a little bit included, yes, because if we really consider the running of these gravity parameters, there is not fixed value of the Planck scale. The Planck scale, yes, is essentially this whole range here of the parameters over which the values of these parameters would evolve towards zero. So this is the effect we take into account. The moment you start running the gravity parameters, we don't really define a particular value of the Planck scale. You just define a functional dependence on the crossover from this UV interacting fixed points to the zero fixed point.
Okay, thank you.
But this is something that we took into account, and this will be in this paper.
Perfect. Thank you.
More questions from the audience? If not, we thank Kamila for the very nice talk.
Thank you very much. It was a pleasure to talk to you.
Thanks a lot, Kamila, for the very nice talk.
Sorry that I kept you so long. I think I a little bit used too much time.
The duration was fine. It was completely fine at all. Very, very nice.
Okay, thank you.
So goodbye, everyone, and see you in the seminar.
Bye-bye.
Bye-bye. Thank you.
Bye.
Bye. Okay, can I?